project is about implementing privacy-preserving techniques and assessing the impact on data utility. In this project, we have implemented three types of privacy-preserving techniques on the dataset, which are k-anonymity, L-diversity, and t-closeness. And the objective is to evaluate the impact of these privacy-preserving techniques on the utility of the data as used in the machine learning models. The importance is to highlight the relevance in today's data-driven world where privacy concerns are paramount. Here is a brief introduction of the dataset. Our dataset has about 50,000 records and 14 features. The features include demographics, economic factors, and social context. The purpose of the dataset is used to predict the income of an individual based on the given census data. Out of all these columns, income is identified as a sensitive column because it contains data about personal income, which is privacy sensitive and can lead to privacy breaches if associated with identifiable individuals. Right, our project. We first take the dataset as the input. To this dataset, we apply each of the three privacy preserving techniques, namely k-anonymity, L-diversity, and t-closeness, to build and obtain an anonymized or privacy-enhanced dataset. We then subject this dataset to machine learning models like logistic regression and random forest, and compare the performance of these models to infer and understand how the utility of the dataset varies with and without privacy preservation. Here are the details about the techniques involved in system design. K-anonymity. This ensures that each record is indistinguishable from at least k-1 other entries regarding the quasi-identifiers. L-diversity. This is an extension to k-anonymity, which requires that each equivalence class has at least L well-represented values for the sensitive attribute. T-closeness. This further extends L-diversity by ensuring that the distribution of sensitive attribute in each equivalence class is close to the distribution of the attribute across the entire dataset. For building anonymized dataset, applying machine learning models and data pre-processing, we make use of several libraries like scikit-learn, pandas, and matplotlib. The main aspect of the design we implement is the data partitioning algorithm to build an anonymized dataset. This algorithm begins by examining the entire dataset. It first determines the range of values for each feature and sorts these values in descending order based on their range. The dataset is then divided at the median value of the first feature. This division creates two new partitions. Next, we check these partitions against the privacy criteria of the three techniques. If a partition meets the criteria, we apply the same splitting process recursively to it. If it doesn't meet the criteria, that partition is finalized as is. This method ensures each data partition maintains privacy while breaking down the dataset into smaller manageable parts. Obtained anonymized dataset subject to the machine learning models yield the following results. Initially, when no privacy-preserving measures are applied, both models perform at approximately 80% accuracy. As the privacy constraints intensify from k-anonymity to L-diversity and finally to t-closeness, the accuracy for both models decreases. For logistic regression, the decline in accuracy is relatively steady and linear, suggesting a proportional relationship between increased privacy and reduced model performance. To confirm this behavior, we subject the dataset to the random forest model, a more robust algorithm, and the trend appears similar, underscoring the consistent trade-off between data privacy and accuracy. This consistent pattern across both models reinforces the conclusion that enhancing privacy indeed comes at the cost of data utility in predictive modeling. Similar trend can be observed in the number of partitions created with application of each privacy-preserving technique. The gradual decrease in the number of partitions from k-anonymity to t-closeness indicates increasing levels of privacy preservation. Presents the outcomes of an experiment where various k values were tested, observing their effect on the model accuracy of the machine learning model. Generally, there is a noticeable downward trend in model accuracy as the k-value increases. This is anticipated as higher k-values corresponding to more generalized data, which can result in the loss of informative details. Interestingly, there is an anomaly observed at k equals to 9 where the accuracy unexpectedly rises. This deviation from the trend might be due to the nature of the machine learning model being used or the unique characteristics of the dataset at hand. It suggests that at this specific point, the balance between generalization for privacy and the retention of useful information might be optimal for the model's performance. However, this is a singular occurrence and might not hold true across different datasets or with other machine learning models, indicating that the observed increase in accuracy is an exception rather than a rule. The final result shows the variation in the number of partitions of the dataset with increasing k-value. The decrease in the number of partitions illustrates the correctness in our procedures and implementation. Addressing the main challenges involve two critical steps: managing the dataset's missing values and pre-processing the data effectively to yield good results. Moreover, fine-tuning the privacy parameters, specifically selecting the optimal values for K, L, and T, presented significant difficulties. Each of these parameters play a vital role in balancing data utility and privacy, and determining the right settings require careful consideration and testing. Project has potential for expansion by incorporating more advanced privacy-preserving methods such as secure multi-party computation (SMPC). Additionally, developing a dynamic system for adjusting the parameters of K, L, and T could make the privacy mechanisms more adaptable and efficient.